session, and I'm happy to welcome Matthew Young, who will speak on the fifth moment of modular alpha.
Okay, thank you. Yeah, thanks to the organizers for organizing such a great conference and inviting me. I should also thank Paul Pollack for agreeing to switch with me. I appreciate it. Okay, so yeah, so this is pretty much everything I'm talking about is joint work with Mehmet Kural. Did I pronounce your name right? Close enough? Okay. All right, so let's go. So this is one of those talks where I think I actually get to state the main theorem on the first page, or the first slide. So, okay, so let's take Q to be a prime, and then kappa is one of these integers, 4, 6, 8, 10, or 14. And I want h kappa of Q to be the set of weight kappa Hecke eigenforms on gamma naught Q with trivial Nebentypus. And the theorem is that if we take the L functions associated to these modular forms and sum up their fifth powers, then the bound is Q to the 1 plus theta plus epsilon, where theta is our best known progress towards the Ramanujan conjecture. So we know that it's at most 7 over 64, but it's conjectured to be 0. So the dimension of this space is proportional to Q. And so we have Q things, and then the upper bound is, I like to, in my mind, I like to think of theta equals 0. And then it's the same number as the dimension. So it's up to this Q to the theta, it's Lindelof on average. So what are these, try to stand forward. Okay, so what are the conditions on kappa and Q? So they make sure that every modular form, every Hecke eigenform in the space is automatically a new form. So there are some modular forms of level Q that could come from lower level. And since Q is a prime, they could only come from level 1. And then there aren't any Cusps forms of level 1 for those weights. And so that it's just sort of a trick to deal with, so that we only have to deal with new forms, and it makes our life easier. I have another paper with Ian Petro where we came up with a Peterson formula for new forms, and we did some moment stuff there. And so one can presumably do that, but the number of letters that would be required in the paper would go up by a lot. So we tried to make it as simple as possible. Okay, so next, all these central values are known to be non-negative by work of Waltz-Bouget, Konen-Zagier, and then Konen. So Konen-Zagier did level 1, and Konen did general level. So from that, then we can drop all the L functions except for one, and we can get a subconvex bound that is bounded by Q to the 1 plus theta over 5. So the conductors of these L functions are all Q, and so the convexity bound is always your conductor to the 1/4 power. So the trivial or convexity bound is Q to the 1/4, and 1 plus theta over 5 is less than that. So that's one of the applications of this fifth moment. Okay, so what was previously known. So in 1992, there are these series of papers by Duke, Friedlander, and Ibanez where they developed the method of amplification and got all sorts of subconvex bounds. And so I think the second one in the series is where they dealt with this level aspect. And so they looked at the fourth moment, but they put in an amplifier. And so if you haven't seen amplifiers before, then I'm not going to say a whole lot because they don't really come up in the talk that much. But it's a way of going a little bit beyond the fourth moment. And so they get this 47 over 192 as the exponent. And so then in 2000, Kowalski, Michel, and Vanderkam got they sort of looked at the same family, and they looked at more general things than just amplifiers. They're able to mollify, and so they were able to prove non-vanishing results and things like that. Then, and then very recently, Belkanova and Frolenkov revisited this twisted fourth moment problem and got a better error term. And so if theta equals 0, their exponent is 27 over 112. And so there's also, I mean, there's so many results on mean values of L functions that I think are interesting, but might, you could do different things. Like you could look at the weight aspect, or you could vary different parameters. You could have Nebentypus or things like that. And those are all interesting, but there's just so many that I couldn't really bring all those things up. And so these are just the results that were strictly about this one family that I seem most closely related to what we did. Okay. So what's going on with this fifth moment? So I want to make the case that this, the fourth moment is what you could call a barrier moment. We don't really have a good name for it, so I've been trying to call it a barrier moment. So it's a barrier for a couple of reasons. So first of all, if you do the fourth moment, you get exactly the convexity bound back if you drop all but one term. So it's just right there. And also, and also it's pretty easy to bound that way. It's like we have sort of general tools like the large sieve inequality for modular forms that don't use very many properties about the L functions, and we just get these bounds. It just sort of pops out. And so it's a barrier in the sense that it's right where we, it's right at the bound that we want, and it's also the tools are pretty simple. And this amplification method is a way to just break past the barrier just a little bit. So, I mean, it's a big thing to just push past it, but it's just pushing past the barriers a little bit. And so there's a analogous problem that I found really interesting is this paper of Conry and Ivanietz from 2000, where so they looked at the same modular form, so it's the same h cap of q's, although q doesn't have to be a prime, it could be square free, and they also look at Moss forms and other things. But anyway, the point is they twist by a quadratic character chi q, where that's the quadratic character of modulus q, which is the same as the level of the forms. And so what that does is it makes all of those twisted modular forms go up to level q squared. And so now the conductor is q squared instead of q. So the conductor goes up a lot when you twist. And so they look at a cubic moment. And so the numerology is that, so if you have q things of conductor q squared, then that's sort of the second moment there sort of matches the fourth moment before. So here, a sharp upper bound on the second moment is what you could call the barrier moment. It's easy to bound the second moment. It gives you convexity. And they were able to do the third moment. So there's a number of other types of, I would say, variants on the cubic moment. Like there's a paper of Ivich that came out around the same time as Conry and Ivanietz, where they looked at level 1 and varied the spectral parameter. And there's a paper of Peng that did the weight aspect. And then there's papers of Ian Petro and myself, like separately and together, that did other types of generalizations or unifications of these. But I would try to classify these as all part of the same collection of moment problems. They're sort of fit together nicely. So now besides those examples, and now this fifth moment, I don't know any examples of a moment problem where we can get a sharp upper bound for for a moment that's one larger than what we would call the barrier moment. Assuming theta equals 0. I like to pretend theta is 0, but okay. So just if you are a fan of the zeta function, then, which everybody should be, then just keeping track of things. So the fourth moment, we have a good upper bound on the fourth moment, which is goes back about 100 years, I think, to Ingham. I tell my calculus students I just always make up history, so I don't know anything. So that may, okay, so you can call me on that later. But anyway, so we have this fourth moment bound, but the sixth moment is wide open. Okay, that would be a big deal if we could do that. So for the zeta function, we can't go up. And the fifth moment is sort of like, for the zeta function, I don't know how to make sense out of that, so it sort of feels like we have to go up by 2. Okay, so one other aspect of how the whole proof goes is that we start with a fifth moment, and then we do a whole bunch of different transformations that I'd like to describe in the course of the talk. But I guess the second to last step is that we get some other sort of family of L functions out, where now, so we have So we get Moss forms, and we get holomorphic modular forms, and we get Eisenstein series, but I'm only writing the Moss forms there. But it's a different family. So we have a sum of their level M1, and M1 is changing. So we've got a sum over a whole bunch of Moss forms of different levels, and they're all sort of combined. And it's it goes down from a fifth moment to a fourth moment. So the fourth moment is, again, this barrier moment, so it's easy to bound it. And, but we get multiplied by this lambda j of q. And q is pretty big, and so it's sort of hard to bound that together. So, but what we can do is just bound the lambda j of q by our best known bound on Hecke eigenvalues of Moss forms. That's where this q to the theta comes in, and then we just throw in a really easy bound on the fourth moment. So that's sort of the rough outline, or like for all I'm talking about is the beginning point and the end point of all the steps. And also, I should say, like this left-right arrow thing, like that's just sort of being extremely sketchy. So we have these integrals. It's not really at a half. We have all these complicated integrals of L functions, and there's all sorts of other coprimality conditions. Again, I'm completely ignoring, but that's sort of the rough idea. And so we've got this kind of connection between two families of L functions. And I really like these identities, or these, in this case, it's sort of an approximate identity. And so there's some, I think Kuznetsov might have been the first one to notice one of these identities. And then Motohashi has developed many of these and proved things really carefully and so on. So, and so these are really powerful techniques. I think these are probably the most powerful techniques that we have for bounding families or moments of L functions, is when you can connect to another family. So like an example would be for the fourth moment of zeta, Motohashi has this identity relating it to the cubic moment of Moss form L functions, and then that gives really strong information. Okay, so I'd like to try to give a broad overview, like really simplified overview of how what happens in the proof, and then as time allows, then zoom in and talk about some of the things that come up. So the first step is we need some formulas for these L functions that are finite sums. So these are approximate functional equations. I want to do this for L function squared and one for the L function cubed. And so I have the squiggly approximation sign, and it means that, so there exists a formula of this rough shape, and I'm trying to display what I think is the pertinent information and not write the stuff that I don't think is so important. So in reality, we have this smooth weight function that decays rapidly, for example, like when m is beyond q or when n is beyond q to the 3/2. I'm not writing the weight function. Also, the coefficients are not exactly, for the L function squared, they're not exactly lambda f of m times the divisor function. That would be the case if the Hecke eigenvalues were completely multiplicative, but they're not. But if you take a couple integers, they're usually at random. They're usually mostly coprime, and so this isn't so far off. And similarly for the cubic power. So, okay. This is a way to reduce the number of letters we have to write. Okay, and then the other tool to start with is the Peterson trace formula. So this is always the basic tool that we have for averaging over a family of modular forms or family of L functions. So the Peterson formula tells us that we can average pairs of Hecke eigenvalues with some weights that we'll just call Peterson weights that are, let's see here if I can get my little laser pointer. So they're basically of size 1 over q. And so the Peterson formula tells us that this is equal to some delta symbol, m equals n, and then with some what you might think of as an error term, but it's really sort of everything. The sum is the sum of Klosterman sums weighted with a Bessel function, a J Bessel function. So this is the usual Klosterman sum that I guess we've seen in some of the other talks. Okay, so our first step is very common in these problems, which is you write down your approximate functional equations and apply the Peterson formula. And so this q to the little o of 1 term up here comes from the diagonal term. Okay, and so one of the reasons I want to display this is just that the way the Peterson weights are scaled is that our goal here is q to the epsilon instead of q to the 1 plus epsilon. The weights are, it's just sort of strange normalization.
You split it into 2 and 3.
2 and 3, right. Yeah. Because we have to get down to 2 lambdas, right? Because the Peterson formula requires you have pairs of Hecke eigenvalues. And so we're sort of stuck with doing something like that. I guess you could do 1 and 4, but anyway. Right. And so we get the sum of Klosterman sums, and then we have, so we have 3 variables. We've got m and n, we've got divisor functions, and we have a Bessel function. So there's all these variables. And usually you want to check your progress and see, okay, if I just bound everything with absolute values, what do I get? And so the best thing we can do with absolute values is to apply the V-bound for Klosterman sums, which roughly says that the Klosterman sum is bounded by square root of c unless there's some coprimality or some big GCD between m and n and c, which is atypical. And so basically you just think of it as square root of c. And so the bound, you just sort of plug and chug this, and the bound turns out to be q to the 7 over 8. We want to get down to q to the epsilon. So it's a massive amount of cancellation that's required at this point. So now let's look at this Bessel function. So if you work in this area, you probably have become friends with the Bessel functions. But anyway, so what's the Bessel function? So there's two ranges of asymptotics for the Bessel function. So if x is going to 0, so if you look at j kappa minus 1 of x, when x goes to 0, it's approximately x to the kappa minus 1. And so that goes to 0 as x goes to 0. And then if x is bigger than 1, then it's approximately it's a linear combination of e to the ix over square root of x and e to the negative ix over square root of x. And so again, that also goes to 0 as x goes off to infinity. So the largest the Bessel function gets is when x is not going to 0 or off to infinity. And so I just write that as x is, I don't know, I think this is /asymp in tech. I just say, I always read this out loud to say x is of size 1. That's what that means. So it's, okay. So in that range, then the Bessel function isn't doing very much, and so I'm just going to stop writing it. But in practice, we have to deal with all the different ranges. And let's also just assume that m and n are close to the largest sizes that they get, because heuristically that should be the hardest case. And so that means that c should be of size square root of mn, so it should be around q to the 5 over 4. So that's just a way to keep track of where all the parameters are. Okay, so now usually what you do next when you study these types of like fourth moment problems, like if you do the amplified or mollified fourth moment, you open up your Klosterman sum, and so you get these additive characters, and then you apply the Voronoi summation formula. So this roughly says that if you have a divisor function weighted by this additive character, then on the dual side, you have another divisor function, but with a different additive character, where your x bar becomes an x. Actually, you have plus and minus, but usually they're both are pretty much the same thing. So let's just look at one. And then so that's a simplification. You get rid of this modular inverse. But then the downside is that your dual sum in this case becomes longer. So the original sum was length q. The dual sum is length c squared over q. We're thinking of c as q to the 5 over 4. And so that means the c squared over q is q to the 3 halves. And so it went from q to the 3 halves. So it's square root of q more terms. And so when you do this, you need even more cancellation than before. We already had a lot that was required of us. And so this is, I don't know. In my mind, it's, you don't really want to do it, but we don't really have any choice. Well, we had to do something. But anyway, actually, this is not the technique that we're doing. I'm just saying that I just want to sort of say a few words about what would happen if we did it the standard way. And then I'll try to do something a little bit different than this. So if you do that, then, so what happens, your Klosterman sum becomes a Ramanujan sum. Ramanujan sums are a lot easier than Klosterman sums. You can evaluate them sort of in terms of divisor sums. And then, so after you do this in a bunch of steps, you get a shifted divisor sum, tau 3 of n versus tau of n plus h. And there's various work on these types of problems. So I think Hooley in 57 was the first to get something about this. Desier got a power saving 1981. There's a paper of Nigel Pitt from 95 where this tau of n plus h he can replace by lambda of n plus h, where those are the Heck eigenvalues of a GL2 cusp form. There's work of Munchi, where he replaces everything by Fourier coefficients of Moss forms. And there's recent work of Topogogulari that probably got the name wrong, pronounced wrong, but that does exactly this tau 3 event, tau of n plus h, and gets a powerful spectral expansion of this. And so it seems that you could probably attack this problem using these techniques if you wanted to. But I want to talk about a different approach. So what we're going to do is, we found this big loss from doing Voronoi summation. We found that unappealing. So what we want to do is minimize our loss right from the get-go. So let's open up tau of m as, open it up as a sum m1, m2 equals m. And by symmetry, let's suppose that m2 is the larger one. And then let's only do Poisson in M2. So I think of Voronoi as opening this and doing Poisson in M1 and M2. And let's only do Poisson in the larger variable. And then, so it turns out, it's sort of a fun calculation with finite Fourier transforms to work out how the Klosterman sum becomes this additive character. So again, it's not a Ramanujan sum. We get this additive character now. So that's an improvement in terms of the complexity of the arithmetical part. And the dual sum is now C over M2. We're thinking of C as Q to the 5 over 4. OK, M2, I'm thinking the worst case is when it's Q to the 1/2. So M1 and M2, with the product, it goes up to Q. I know all these variables will make you dizzy. I'll try to keep reminding you. I had to make a chart just to keep tracks, OK, when writing this. But OK, so M1 times M2 went up to Q. And so the worst case is when they're roughly equal. And then that means M2 is like square root of Q. So now the sum has length Q to the 3/4 instead of Q to the 1/2. So it's worse than before. Again, oh, sorry.
What were you doing in that step? Were you breaking into confidence classes?
Yeah, Poisson summation mod C.
What happened to the sum of C?
Well, so I didn't write. I'm just looking at the inner sum. I'm trying. I don't want to keep writing these massive expressions. I'm just saying, OK, now let's look at the inner sum and say what we're going to do to that, and then put it back. Trying to conserve how many letters I have to write in any given slide. OK. So then, so now if we look at this additive character, it's we get this E of M1 and K bar over C, and then now this is ripe for using this reciprocity formula that many people have been using. And so basically, it's basically the Chinese remainder theorem. Okay, this is an elementary reciprocity law. And so it lets us replace, basically, we think of it as you replace K bar over C by C bar, by the C bar over K with this correction factor, this E of M1N over CK. Okay? And now if everything is close to if all the variables are as big as we think that they are, I don't know if that's right. If all the variables are close to their maximal sizes, maybe, then that means this M1N over CK is roughly 1. And this is a pretty common feature when applying this reciprocity law. And so if so, then this extra factor, this E of M1N over CK, isn't really doing a whole lot. It's not causing us any problems. We're just going to sort of put it in with the weight function that I haven't been writing anyway. Right. And then now the huge gain is that the modulus is reduced from Q to the 5 over 4 to Q to the 3 over 4. So that's the improvement. Now, in reality, of course, K it's not always of size Q to the 3/4. It could be smaller. And then when that happens, there's two effects that are sort of competing. So on the one hand, when K is smaller, this thing becomes more oscillatory. And that makes the analytic part more complicated. But the arithmetic part becomes simpler. The modulus is even smaller. So these things sort of counterbalance. And so, yeah. OK. So now we reduce the modulus. And now we can try to apply more Poisson summations or Voronoi summations or whatever you want to call it. So when I say Voronoi summation for this tau 3 event, I really just mean open the sum up and apply Poisson in each variable. Now it's Poisson mod K instead of C. And it's another fun calculation with finite Fourier transforms to work out if you apply 3 times Poisson summation to something with this, this particular additive character, then you get a different Klosterman sum back. But now we've got this M1 bar. And the modulus of the Klosterman sum is K. So after all these moves, then the moment that we're working on becomes this thing. So this tau 3 of P, like that's really, we have 3 variables, P1, P2, and P3, let's say. Those are the dual variables to N1, N2, and N3 when I open up this divisor function. And then they sort of naturally come together as a product. So that's why we grouped it as tau 3 of P. But the main thing is that this length of summation of the P sum is now less than before. So originally N was Q to the 3/2, but now it's down to Q to the 3/4. And that entirely came from the reduction in the modulus K. So, so now at this point we've made some progress because the V-bound gives us Q to the 5/8. So that's good. It started out 7/8, and then we took a loss. So then we got it back with some more. And then and now you might be tempted to apply Poisson summation one more time in M1 because you would get a savings in the length of summation from that one also. But the problem is then the Klosterman sum would become a hyperklosterman sum. Okay, in Klosterman sums we have a lot more structure for dealing with them, which we'll get into on the next slide. Whereas hyperklosterman sums we don't have as much technology. So there is a paper of Nigel Pitt that gets some bounds for sums of hyperklosterman sums, but it's harder and the results aren't as strong. So we're going to avoid doing that. Okay, so what we have the technology that we have is the Brueggemann-Kuznetsov formula. And so this was generalized in a paper of Desier and Ivanets from 1982, where Brueggemann and Kuznetsov, from what I remember, stuck to level 1, so stuck to SL2Z. And Desier and Ivanets did general levels, and they allowed for more general cusps of their Fourier coefficients, and you got more complicated Klosterman sums. So I've got this SAB, which I don't really want to define, because if you haven't seen it, it's just sort of scary. And if you have seen it, then you sort of know what I'm talking about. But it's some sort of generalization. So needless to say, if the level is 1, then this SAB is the usual Klosterman sum. Okay, and so A and B are cusps for the group gamma, and these new A of M's and new B of N's, those are the Fourier coefficients of Moss forms when you expand around the cusps A and B. So this is, you can think of as a generalization of the Peterson formula. So the Peterson formula, well, we had C congruent to 0 mod Q, and that's like a particular choice of cusp. So if you pick the cusp infinity for A and B, then you get C congruent to 0 mod Q. And this, one of the nice things about this formula is this F, you get to pick it from a pretty wide class of functions. You just think of it as arbitrary, smooth enough, and you need it to converge absolutely, and so on. But it's pretty arbitrary. Whereas the Peterson formula forced F to be a J Bessel function. And so if you allow for more general functions on this side, then it expands the right-hand side. It's not just holomorphic modular forms, but you get Moss forms and Eisenstein series, and also holomorphic modular forms back. Okay, so now, here's a question that is sort of an annoying thing, that if you're given some sort of sum of Klosterman sums and you want to apply the spectral theory to it, you have to recognize it as something to which you can apply the spectral theory. So you have to recognize it as an SAB-MNC, or maybe a sum over cusps or something like that. And the usual way that this works, it goes back to Desier and Ivanets. They just picked all sorts of cusps and calculated Klosterman sums and saying, well, now and sort of made a table, and then now you look for, if you're handed a Klosterman sum, you look for it in the table and say, oh, aha, it goes back to this pair of cusps. But there's no way to go backwards. Okay, so the calculation of the Klosterman sum is sort of complicated. So yeah, so Desier and Ivanets worked out many cases, but not everything that we wanted. And there's a nice paper of Blomer and Milosevic that showed how you can decompose pretty general arithmetic functions. So you can have C congruent to A mod Q, general sum like this. So if you can pick out a C in a residue class mod Q, then basically you can do anything you want. Like you can have C coprime to something or other, C congruent to whatever you want, mod something else. And so they decompose this into these Klosterman sums attached to cusps with Nedman-Tippis character. So we found it really reassuring to have this in the background that we knew in principle something should exist. But we ended up not using their formulas. So let's go back to this Klosterman sum. So we want to recognize this S of P, C, M1 bar. We've got this bar here, K over K as a Klosterman sum. And actually, in reality, I've been waving my hands. There's various other really annoying conditions, like extra coprimality conditions, more congruences, and things like that. And so, okay, so if you get this, then what you do is you look in Desier and Ivanitz and you find an example. So they work this out. So you pick the cusp. One cusp is infinity. The other is 1 over r. And where your level is r times s, so r and s have to be relatively prime. And then you get your Klosterman sum, but you've got this additive character. It's sort of annoying that that's there. We don't have that, and actually this potentially this would cause some major problems, actually, if that was there. But I should say that there's this relies on a choice of scaling matrices, and this is something that I've avoided thinking about for a long time in my life. Scaling matrices and choices of cusps and everything, but we really had to delve into this for this project. So a scaling matrix is something that it's a matrix that lets you convert, it's sort of like a change of variables from your cusp A to infinity so that you can work around the cusp infinity. So you always sort of want to translate to infinity. And there's a choice in how you pick your scaling matrix. And depending on your choice, so going back to the Kuznetsov formula even, depending on your choice of scaling matrices, the Klosterman sum changes. So the notation is SAB, but it actually should be, it doesn't just depend on the cusps, it depends on the choice of scaling matrices. Oh, that was fast. And then also on the spectral side, where we have these Moss forms and the Fourier coefficients at A and B, those also depend on the choice of scaling matrices. So on both sides, and to compensate perfectly for each other. So it's just an issue that I hadn't really thought about very carefully before, but it turns out to be pretty important for this. So with this particular choice of scaling matrix or matrices, then that's how you get this Desier and Ivanitz formula. Okay. So, but one thing that we realized while working on this is that what you should do, if you have the choice, you should choose your scaling matrices to be Akin-Lehner operators. Okay, so it helps guide you on what's a good choice of your scaling matrices. So the reason you would like them to be Akin-Lehner operators is that, well, if the Moss forms or the modular forms that you're working with are eigenfunctions, or say if they're new forms, then they're eigenfunctions of the Akin-Lehner operators, and which are involutions. And so that means the eigenvalue is plus or minus 1. And so what that amounts to is saying that the Fourier coefficients at any cusp equivalent to one of these, okay, so I'm trying to put too much into one sentence. Okay, so let's decide that, let's declare that an Akin-Lehner cusp is one that's equivalent to infinity under an Akin-Lehner operator. And so if you have a new form or something that's an eigenfunction of an Akin-Lehner operator, that means that the Fourier coefficients at infinity are up to plus or minus 1, the same as the Fourier coefficients at your cusp A. And so if you pick a basis where the Fourier coefficients at infinity are multiplicative and have nice properties, then the same thing holds automatically for these other cusps. If you just take an arbitrary cusp, then the Fourier coefficients can be a lot more complicated. So that's the reason why we always want to pick Akin-Lehner operators to be our scaling matrices. And so what we did was we basically worked out in pretty gross generality for these Klosterman sums. So you take arbitrary Akin-Lehner cusps, A and B, and we can throw in a Nebentibus character, chi, and then we worked out a formula. So this is in quotes because I'm not stating the formula because, again, it has lots of letters, and it's not what we need for purposes of this talk. But if you ever wanted to look up, if you ever encounter some Klosterman sum and you want to hope that it occurs somewhere, then you could look at our paper, and we have pretty general formulas. So as a special case, so I will state a special case. So if n is r times s, r and s are relatively prime, and then instead of choosing sigma 1 over r like Desier and Ivanitz did, but you choose it to be an Akin-Lehner operator, then you get exactly what you want without this annoying additive twist. So actually, we could have used this Desier and Ivanitz formula, but then we would have gotten the Fourier coefficients at this twisted cusp, and it would not have been It would have been multiplicative after the shifting by that extra additive twist that was there. And so it would have been a little more complicated, or we probably wouldn't have even noticed that. So this was really important to have multiplicative Fourier coefficients after Kuznetsov. Okay, so basically this type of thing is what lets us get this bar, and there's no additive twist, and everything is multiplicative. So everything is as nice as it possibly could be. And also we don't need to sum over any Dirichlet characters, any Nebentipus characters. It's all just the most efficient possible thing, which is just a single pair of cusps.
There are some cusps which are not Atkin left,
Right.
But that Blomer-Milosevic theorem, you're saying that theorem could be, you can represent that sum mod Q by only using Atkin-Leffner's cusp?
I don't think I'm saying, I don't know what I'm saying. I mean,
In this case, like you're saying,
yeah, so if A and B are Atkin-Lehner cusps, well, okay, so we worked out all the Klosterman sums for general Atkin-Lehner cusps. What Blomer-Milosevic did was work out if you want to get a C congruent to A mod Q, you can decompose it using, well, let's see. Yeah, I'm not sure if they're Atkin-Lehner cusps. You didn't need them. Well, you want that.
We did have character twists.
Right, you put in the character twist, right. So you summed over all, you had all cusps, right, not just Atkin-Lehner cusps.
Yes, we used
Yeah.
all of Q, and Q was arbitrary.
Okay, yeah. So, I mean, the way I think about it is if you can restrict to Atkin-Lehner cusps, then that's a good thing. Because then things will be multiplicative afterwards. Otherwise, you can't do a whole lot. You might not be able to do as much with the Fourier coefficients. Okay, so another thing we did, just as part of this calculation, was we worked out the Fourier coefficients of an arbitrary Eisenstein series. So here A is arbitrary, and we worked out the Fourier coefficients around an arbitrary Atkin-Lehner cusp. So it's the kind of thing that I often wished existed, but I couldn't ever find it, and so we did it. We need it for other things in the paper too that I probably won't talk about. Okay, so now regrouping. So we were back here. So we've got this sum of Klosterman sums, and now we can apply Kuznetsov to that and get, and then we'll get Fourier coefficients, and so that's the next step. And then we're almost done. So once we get to Fourier coefficients, now these, I wrote them, so it should be these, 1 over r and infinity, but really the Fourier coefficients are essentially the same. So I'm just writing them at infinity now. And then these are multiplicative, and this is extremely important because this lets us express this type of thing in terms of L functions. And so one thing that's going on, one condition is the C that's congruent to 0 mod Q, that we haven't really done anything with that through the whole, that's still that same C is congruent to 0 mod Q that came from Peterson. And then now that's going to come out here because by multiplicativity, we're just sort of going to pull out the qth Hecke eigenvalue of this Moss form. And so basically, this is why you get lambda j of q times the fourth moment of this family of L functions. So that's sort of the broad, really sketchy outline of all the steps. Right, and I think I already said this earlier, that we used that that's bounded by q to the theta and used the easy bound on the fourth moment. Okay, so I think what I had next, yeah. So I wanted to talk about some aspects that came up that I completely shoved under the rug so far and that I am kind of interested in. So one of the things that comes up in this problem and other moment problems that I've looked at where you need a lot of cancellation is that we need to really understand oscillatory integrals in a good way. So here, suppose we have some oscillatory integral. So actually, the upshot of all this is that I want to show you some results that show you that you don't have to worry much about oscillatory integrals. And so hopefully, I hope they're written in an easy to use way, so that so people can use them without worrying too much about it. But okay, anyway, so I'm getting ahead of myself. So imagine you've got some oscillatory integral. So phi is call that the phase function, and w is some smooth function. So everything is smooth. And something to keep in mind is something like, what if phi, this phase is a constant times square root of t minus lambda t. So like that would come in if you took a Fourier transform, maybe of a Bessel function, right? Because the Bessel function sometimes has this type of phase. and then w. Everything is actually a family of functions. I'm just writing it for phi and w, but these always come in families. You've got all these parameters, and you have to just keep track of uniformity in everything. So the first thing is, if phi prime is never small, like if the first derivative of the phase is not too small, then generally what you can do is just integrate by parts a million times and prove that the integral is really, really small. So of course, you don't actually want to integrate by parts a million times, so you have to sort of come up with a general pattern for how you can do it an arbitrary number of times. And that's, it's sort of calculus, but it's complicated. So that's something, we have a result like that. I'll get to that in a second. And so basically, the way that you can use this is say, well, unless there's some conspiracy with the variables, like your a and your lambda and your t, then this integral is just really small. So that's like the first step. It sort of lets you clear out some, a lot of the cases of the parameters, and then zoom in on the ones that are important, where it's possible that phi prime is small. So it could be 0 somewhere. Okay. So that's the first step, sort of like a cleaning step. So next, let's suppose that phi prime is small. So let's say it's 0 somewhere for some point t0. So t0 is defined implicitly by this equation, phi prime equals 0. And then the stationary phase method tells you if the second derivative is not too small, then it lets you get an asymptotic formula. So these types of results, this kind of asymptotic appears in different sources, like Ibanez and Kowalski, or Huxley has a book. He has some results like, if W is 3 times differentiable and different, all these complicated conditions. And one of the features here is that you get exactly this original function W evaluated at t0. Okay, so that's your weight function. But the problem is that this error term is not that. It's pretty good, but for like if like in this problem we needed to save q to the 7 over 8, that error term isn't good enough, and so we need to improve this, and we should do this systematically and just really figure out what's going on. So there's this paper I wrote with Valentin Blomer and Rizwan Khan that works out the full asymptotic expansion. So there's some sort of nice function that I put in quotes here. There's a nice function that lets you basically, it's all the main terms that could possibly appear, and then with a really small error term. And now f, you don't really want to know what f is. But basically, if you know the stationary phase method, what you're doing is you're sort of in your phase, you're sort of doing a quadratic approximation, and then everything else, like everything that's cubic and higher degree polynomials, you sort of throw that into your weight function. That's your new, and that's part of your new weight function. And then you do some kind of analysis there, and it turns out you get this expansion. So the sum over n is an expansion, and you've got this function g. That's like your f with this part of the phase, like the cubic and higher terms. You differentiate that 2 times n many times, divide by phi double prime to the n power. I don't want you to get much out of this except just think like, wow, I don't really want to work with this if I can help it, okay? One thing in math is you want to know what property something has. You don't want to know what it is, okay, a lot of times. So you don't want to use what f is, you want to use what properties it has. And so in this paper with Blomer and Kahn, we worked out some, like if you differentiate f with respect to y, what are the properties it has. But what we didn't work out, which is pretty important actually, is that if we have multiple variables, then how does this f depend on all these other variables? So this process of this complicated process of how you form f is sort of hard to keep track of everything. So before I state the result, I want to say what nice means. Okay, so this is another thing I want to try to advocate for. So what is nice? So I like the idea. I like using the word inert. So an inert function doesn't do much. It just sort of keeps on doing what it was already doing. So let's suppose we have a family or a collection of functions, and let's just, for the sake of argument, say they're supported on dyadic intervals. You could always apply some kind of dyadic partition of unity to get to things like that if that's not, if your particular functions don't have that property. But anyway, so then let's suppose they're supported on dyadic intervals, and then basically it's a derivative condition. So actually we could say they're x inert, but for now let's just take x equals 1. So it just means that there's some constants that they may depend on the family, but they're independent of which element of the family you're in. And then the derivatives, it basically behaves sort of like a polynomial. You differentiate it, and you just bring down a power each time. So it's not doing very much. And a good example to have in mind is just, what if you just take some fixed function once and for all, this omega, and then just rescale it by all these parameters x1 up to xd, and then the family is just depends on these x1, capital X1 up to capital xd's, and then all these constants are independent of your capital x1 up to xd. So that's the kind of thing I'm thinking about. So I never want to use what properties, like what my weight functions are. I just want to use what derivative bounds they have. That's always the goal here. So you just keep track of derivative bounds forever. Okay, so now the new theorem, which is sort of built up, started with this Blomer and Kahn paper, and I made some progress myself, and progress with paper with Ian, Petro, and this fifth moment paper, which says, again, I didn't want to write down all the technical conditions on the derivatives, but roughly this is what it's saying, is that suppose you have inert functions or inert family of functions, and you need some conditions for stationary phase to hold. So there's always some condition for stationary phase, right? So supposing that the conditions for stationary phase hold so that, let's say in terms of T1, let's just look at one variable at a time, so T1, with uniformity in all the other variables. So let's say you could do stationary phase in T1, then this function, f of T0, that you get is still inert. So T0 is an implicit function of all the other variables now, because it's defined by this phi prime equals 0. So you have one fewer variable now, but the function remains inert. So it's some sort of closure property under stationary phase. So if you start with inert functions and you apply stationary phase, then it stays inert. And so that's basically all you have to just say, is that you just say your function's inert, and then you don't have to say much more than that. So it's a really concise way to keep track of all these derivative bounds, I hope. And the proof is just some gigantic calculus problem. You just keep track of differentiating all sorts of things and all sorts of variables. And it's something you just want to do once in your life and never have to do it again. And I hope none of you ever have to do it. And then you could just use this result if you need it. So, OK. So the next thing, the other thing I want to zoom in on is main terms, or lack of them. So in the whole discussion, like the whole sketch, I never talked about any main terms. And so actually, what I want to point you to is that when we did this Poisson summation formula here, so this p variable, we said p was of size q to the 3/4. And so actually, remember, this is like p1, p2, and p3. So those are the variables after Poisson summation in that. And so usually what happens is that main terms come from the 0 frequency. Okay, so when one of those p1 or up to p2 or p3 are 0. So right, so Poisson summation, so we're applying Poisson summation, and this is the Poisson formula. And when you plug in nu equals 0, that's what I would call the 0 frequency. Then often that gives you a main term. And if you just look at this, it's sort of an approximation of your sum by the integral. So plug in nu equals 0. And so far what I said, I completely ignored all of these 0 frequencies. And when we were working on this, we ignored them for a really long time until, because we thought, oh yeah, that should be pretty easy to deal with 0 frequencies. But it turns out it's actually pretty tricky. So so a 0 frequency is when one of the p's is 0, not necessarily all 3. And so when you put in the trivial bound on these 0 frequencies, it turns out the bound you get is q to the quarter plus epsilon, not q to the epsilon. And so q to the quarter is just completely worthless. Like it's consistent with the convexity bound, and we could prove it. We could have proved it in one line at the beginning, applying the convexity bound to one of the 5 L functions, and then apply the easy fourth moment bound. So basically, we're just completely dead if we can't get rid of this main term, this thing that looks like q to the quarter. I mean, actually, if there was a main term of size q to the quarter there, it would disprove the Lindelof hypothesis. So that would be good. I mean, well, that wouldn't be good, but it'd be exciting. But actually, it would disprove known subconvexity results, and so that's even worse. So we know that they can't actually be there. I mean, we could worry that, well, maybe they're not q to the quarter, but they're secretly like, q to the just barely enough to be consistent with the known subconvexity results, but not any better than that or something like that. So, but what should happen is that they all basically cancel. And it's really tricky to prove that they cancel. I mean, in these other works on the twisted fourth moment, they also had to deal with a really complicated, deal with these main terms. They come out in a different way because they're solving shifted convolution problems, and just the combinatorics of how the main terms come out is completely different. And so we couldn't really compare. Okay, so there's these main terms that we're calling fake because we know they can't actually be there. But proving that they're really not there it takes some work. And so to try to get the idea across of what's happening, I came up with a really simple toy example, which might be overly simplified, but okay. So that's okay. So let's say we have a weight function v of x, which is given by a Mellin integral, where this g function, this capital G, is holomorphic. It's even, rapid decay, and g of 0 equals 1. And so if you're used to using the approximate functional equation, then you're used to being able to make a choice like this. You always have this choice of this function g inside the approximate functional equation. Okay. Now, suppose we had this just as like a fake main term, or a potential main term. Suppose we have a sum 1 over square root of n, v of n over square root of q. So this is, I mean, we get things that sort of vaguely resemble this after lots and lots of, analysis. So, okay, so this v function, you can analyze this by shifting contours around. So if x is less than 1, then you can shift the contour off to the left. There's a pole at s equals 0. So v of x is approximately 1 for x small. And then if x is bigger than 1, then you can keep the contour where it is, or you can move it off farther to the right. And so there's rapid decay for x bigger than 1. And so if you just put those two things together, it tells you that this sum s is bounded by q to the 1/4. And I scaled it so it's exactly the same q to the 1/4 that we're trying to get rid of. Okay, so I mean, there's not much you can do. I mean, v is just this function. I mean, if you just, well, okay. But what you can do to analyze this further is you could go back and just plug in the definition of v into the sum, and then reverse the orders of summation and integration. And what you get is you get this integral with zeta of a half plus s, g of s over s, and then times q to the s over 2. So now you do the usual thing, move it over to the left. There's a pole that you had at s equals a half, and that gives you exactly this q to the 1/4 times g of a half. And then if you just stop at epsilon, you get big O of q to the epsilon. That's what we want, is q to the epsilon. So, so now it's perfect. Within all the choices that we were allowed to make on g, we're perfectly allowed to pick g of a half equals 0, and to make this term equal 0. Okay, which sort of seems like cheating, right? I mean, but yeah, I mean, I guess from working in these problems, I've gotten used to at least the fact that only g of 0 matters, and you can always choose g to be 0 at any other point. And it actually really helps simplify main terms by making these choices as sort of cutthroat as possible. You just try to cancel everything that's not forced to cancel. So the only thing basically that you're not allowed to do is change the value g of 0. G of 0 has to equal 1. So right. So one thing I guess to regroup on is, so this g of a half over half by the Mellin inversion formula is just the integral of v of x over square root of x. So g of a half over a half, which is the same as g of a half vanishing, means that this integral vanishes. So the sum is approximated by the integral, and the integral happens to vanish. But if, it's some sort of fact that it's all because we had 1 over square root of n. So if we had 1 over n instead of 1 over square root of n, then we couldn't do this, because then the poles get, the pole of zeta gets piled up on the same place as this 1 over s pole that we have. And so then you can't separate them. And so this is provably log q, or constant log q. And so you can't use this trick to get rid of this. So the true main term should be more like this type of thing. And so it's one way to systematically from the beginning help you keep track of what should be a true main term and what's a fake main term. So in a way, it's almost like we're trying to L functions, like you choose your approximate functional equation to get your preferred value of your L function. And then in a way, like this weird thing that we were getting, this 1 over squared event, it's like an approximate functional equation for a different value of the L function, like somewhere else. And so so that's sort of the wrong thing. I don't know, that's really vague. Anyway, so that's all I wanted to say. I'll stop here. Thanks.
Any questions?
So I have a question about your discussion of stationary phase.
Uh-huh.
So one problem I've read about trying to estimate the partial sawtooth of some L function. And you write down this contour integral, you shift it, then you recognize somehow that it's a Bessel function, and then there's some result that's known that it's equal to the cosine of something plus some smaller error term. I'm curious if your stationary phase method might be able to show that directly without going to a Bessel function.
I think that's a little more technical for me to answer right now. I'd have to look at it to see if but I mean, often it's the case that you can do these contour shifting methods that are sort of equivalent to stationary phase secretly. So I don't know. I guess I'd have to look at it. Maybe we can talk afterwards.
Other questions?
So would the actual main term come from what you call the fake main terms rather than what you showed at the very first slide of the proof?
Well, it would be a really interesting thing to try to work out all the main terms in this problem. It's hard enough trying to get all the main terms when you do the fourth moment. And it's not quite clear where they all come from. I mean, it's possible that there's a main term coming from this dual moment that we have. Oh, maybe not. Yeah, maybe not. Maybe this should be 1 over root q times. Yeah, but you just have to look really carefully to see where all the main terms are. But the fake main terms, I can't remember if there's possible q to the right, like q to the epsilon true main terms secretly hidden in those. That may be true. I'm not sure. Yeah.
Anyone else?
And you think maybe hypothetically using some of those words you cited on tau 3 and let's say tau then,
Yeah.
you could say treat L of F tensor cuspal GL3, L of F tensor cuspal GL3.
Yeah. Let's see. Right. I mean, yeah. So I guess I think all roads lead to Rome. So I think if you follow this kind of approach, you sort of get to the same family of L functions. I would have to think more carefully if you replace these by Cusp form coefficients, if you could still get to the same thing. We used this factors. Yeah, this is I sort of shoved this under the rug, but like this tau 3 of p here. S of P, C, M1 bar K. Yeah, actually, yeah, this is a really important point. So this, when we, after we applied Kuznetsov, I reshuffled it. So where did this go? Yeah, so now I reshuffled it, so this P1 moved over here, and P2 and P3 I put over there. So if I had a GL3 Cusp form, I couldn't rebalance them. And then that would cause, you wouldn't get just the fourth moment anymore, and it might be a lot harder to bound it. So it's possible one could do something, but it's not quite clear it would go the same way. So there's some additional complications that happen.
If there are no further questions, let's go ahead and thank our speaker again.